Welcome everyone to this second session of the National Colloquium for Artificial Intelligence. This colloquium is an initiative organized by the Mexican Society for Artificial Intelligence, the Artificial Intelligence Alliance for Mexico, the Mexican Academy for Computing, and the other researchers groups involved with artificial intelligence, like CINVESTAV, SIC, Instituto Politécnico Nacional, UNAM, etc. Today, we are honored to receive to Professor Baldi, Pierre Baldi. Professor Baldi will present the talk entitled Artificial Intelligence, Deep Learning, and Virtualization. Right now, let me to present a very short curriculum about the huge curriculum of Professor Baldi. Professor Pierre Baldi is a distinguished professor from the Department of Computer Science Director, Institute for Genomic and Bioinformatics, Associate Director, Center for Machine Learning and Intelligent System from the University of California, Irvine. Pierre Baldi earned master's degree in mathematics and psychology from the University of Paris and a PhD in mathematics from the California Institute of Technology. He is currently distinguished professor in the Department of Computer Science, director of the Institute for Genomics and Bioinformatics, and associate director of the Center for Machine Learning and Intelligent System at the University of California, Irvine. The long-term focus of his research is on understanding intelligence in brains and machines. He has made several contributions to the theory of deep learning and developed and applied deep learning methods for problems in the natural science, such as the detection of exotic particles in physics, the prediction of reactions in chemistry, and the prediction of protein secondary and tertiary structure in biology. He has written 5 books and over 300 peer-reviewed articles. He is the recipient of the 1993 Leo Allen Award at the GPL, the 2010 E.R. Cayaniello Prize for Research in Machine Learning, and the 2014 Google Faculty Research Award. He is an elect fellow of the AAAS, AAAI, IEEE, ACM, and ESCB. Without any more to say, please, Pierre, the floor is yours.
Thank you. Thank you very much for the invitation to talk to you today. I'm going to talk to you about AI, in particular deep learning, which is today the main technique that is used in AI, and virtualization, and what are the connections between these ideas. Everything I'm going to say is contained in these references for those of you who are interested in the topic. So there are a few articles, and then there is a book that should come out. Actually, it is being delayed, so it will come out, I think, in March 2021 on deep learning and its applications in the natural sciences. So the roadmap for the talk today is, first, I'm going to go over AI and deep learning and just go through a few historical points. And I will discuss some of the questions that are raised by those historical points. Then I will introduce the concept of virtualization and why it is, I think, so important for computer science and for AI. And I will show how ideas of virtualization can help us address those open questions, solve them, and also give us some directions for future research. So let me start with a few historical points and remarks. And to begin with, I want to go back to the early 50s, late 40s, early 50s, to Donald Hebb, who was one of the first to think about possible learning rule, learning mechanisms. And he wrote a book on this topic where there is not a single equation. But somewhere in the book, you find this sentence that has become quite famous, and it's, to paraphrase it in a short way, the idea is that neurons that fire together wire together. So it's the idea of correlational learning, where neurons that have correlated activities should strengthen their connection, right? And so you can write mathematically one simple way of writing the Hebb idea is to say that the change in the weight between neuron I and neuron J should be proportional to the product of their activities. That's the so-called simple Hebb learning rule. And it is an attractive and interesting rule, but if you take a complex network for, say, computer vision, no one has been able to get those networks to work using this simple rule, and there are reasons for that, and that's one of the issues we're going to discuss in this talk. A few years later, Fukushima came up with the so-called neocognitron architecture, which is basically a convolutional neural network. So inspired by the work of Yuval and Wiesel in the 60s, basically Fukushima thought about building architectures, neural architecture, where the lower layers basically are implementing convolution operations, filters, edge detectors, etc., that can be applied to the incoming image in order to produce translation invariant recognition of objects in those images. And that's pretty much the sort of architectures we're using today in computer vision. The only problem was the learning. How do you learn the weights of such an architecture? And if you read the papers by Fukushima, he proposed to do it by Hebbian learning. And no one has been able to train a convolutional neural network with Hebbian learning for computer vision tasks. The algorithm that works for learning, as everyone should know, is backpropagation or stochastic gradient descent, where basically you have some kind of error function at the output in supervised learning. And the idea is to train the weight to minimize this error function. And this is done by gradient descent. And when you derive the equations for gradient descent, it's a straightforward application of the chain rule. You find that the way you change the weights in a deep connection between neuron J and neuron I is by this formula, which has a learning rate. It has the output of the presynaptic neuron. So in that sense, it's very Hebbian. But then there is another term, which is called the backpropagated error at the neuron I here. And this backpropagated error has to be computed starting from the top layer and then propagating the activity, the error activity in the reverse direction, in the backward direction. And basically, every time you traverse a layer in the backward direction, you have to multiply by the same weights that you use in the forward direction. So basically, in a matrix format, you get the transpose of the forward matrix. And then every time you traverse a layer of activations, you have to also multiply by the derivatives of all the activation functions. So if you write the rule in matrix form, you get the expression at the bottom, where again, in order to change the matrices of weights between layer H-1 and layer H, you have an outer product of the activities in the previous layer, layer H-1. So this is this term here. And then you have the backpropagated error, which is an alternation of operations where you have matrix multiplications by the transpose of the forward matrices. And then the F's represents the derivative of the transfer function of the activation functions in each one of the layers. And at the top, the error in general is t minus o under very standard assumptions that I'm not going to go over. Okay, so that's the algorithm that works. And already in the late 80s, early 90s, we were able to train, us and many other groups were able to train convolutional neural networks like Fukushima's network on computer vision tasks. The most famous application is digit recognition by Yann LeCun and collaborators. But for instance, in this case, with Yves Chauvin, we were applying these architectures to fingerprint recognition. This is what you would call today a Siamese architecture, where you present two fingerprint images. And the goal of the convolutional architecture of the CNN is to decide whether yes or no these two images come from essentially the same finger or not, right? So it's a classification architecture that you can train, and already in the late 80s, early 90s, we were able to show that this was working quite well. Today, we have an explosion of such applications in the biomedical sciences and across all areas of technology, self-driving cars, etc. I'm just going to very briefly show you an application that we have in biomedicine for colonoscopies, which is given an image of the colon, try to identify whether there is a polyp. You can see here a polyp, and draw a bounding box around the polyp. So we can do those tasks very well. You can see the ROC curves here, given a training set of such images. But also very interestingly is that the training may take some time, a couple of weeks on a few GPUs. But once the system is well trained, it can produce outputs very fast in something like 20 milliseconds. So even if we're using video, which is what colonoscopy is about, we can still use this network that is trained on still images, on individual frames, to recognize and locate polyps. I hope this is going to work. I have a video. Let me know if you don't see anything. Otherwise, I'll assume that you are seeing this video. And you are going to see this sort of AI in production mode, where you are seeing clips, video clips from actual colonoscopies. And you can see our system is putting bounding boxes around polyps. And this system is actually a derivative of this system, I should say, is currently undergoing clinical trials. So it's being used in real life, in real applications. Okay, I think you get the idea. I'm going to try to go to the next slide. Another application, a recent application of deep learning is to somehow reasoning, right? You may think that it's only good for perceptual things, for computer vision or speech processing, things like that. But you can also, in some sense, do reasoning with, for instance, deep reinforcement learning. So this is an application to solve the Rubik's Cube. And you're going to see a Rubik's Cube and then a scrambling of the cube. And then the AI, again, the deep neural network that was trained to solve the Rubik's Cube, produces the solution here, a sequence of move. So R is, for instance, turn the right face clockwise, R prime, turn the right face counterclockwise, etc. And you apply those moves, and it puts the cube back into the solved state, right? So these are just examples of things you can do today with deep learning. Of course, there is many more. And what I want to point out is that these brief historical points and demo lead us to a few open questions. The first question is, why do we seem to have only two learning rules, right? Hebb rule, gradient descent, backpropagation seem to be the main rules in the literature. Those of you who are expert know that there is a few other things. There is things like Oja's rule, etc., etc. But by and large, these are the main rules. And so the question is, what is the space of learning rules? Are there maybe better learning rules out there that we should try to find, etc., etc., right? A second question is backpropagation Hebbian? In a sense, it looks Hebbian because it is a product of two things, so there is sort of a correlation idea there. But the backpropagated error is not the activity of the postsynaptic neuron. So in that sense, it's not Hebbian. And we need to resolve this tension and better understand this question. The third question is why Hebbian learning failed in the neocognitron and pretty much any other CNN or any other deep learning application, right? What is the reason behind that? And then in backpropagation, we saw that if you write down the mathematical equations, in the backward pass, you have to use exactly the same weight that were used in the forward pass. And this seems very difficult to do in physical neural systems, in particular in biological systems. It's virtually impossible to have neurons running in both directions that have exactly the same synaptic weights. So if you think that there is something biological plausible in backpropagation, this is definitely a problem, and one has to think of ways for addressing it. So what I'm going to do now is to solve these four questions through the concept of virtualization. So let me say a few things about virtualization. Very simple idea. It's the mapping or simulation of a computing process onto a different computing process, possibly with different hardware substrate, etc., producing the same overall results. So it's a very basic idea. You're all familiar with it. I can argue that it's at the center of computer science, because what is computer science if it's not, taking let's say, an algorithm, a computation, adding two binary numbers together, for instance, and mapping this sort of abstract mathematical concept onto the dynamics of some hardware substrate, whether it is an abacus or transistors or DNA computing or quantum computing. You have a mapping from a sort of abstract entity onto the dynamics of a physical system, right? So virtualization is really at the center of computer science. When you study Turing machines, you definitely go through virtualization, because you start in a typical course with the development of special purpose Turing machines for adding two binary numbers or for detecting whether a binary number has an even or odd number of ones, the parity problem, etc., etc. So you learn how to build such machines, and then you move to the next stage where you introduce the universal Turing machine, which is a machine that basically virtualizes all these special purpose Turing machines. So again, the concept of virtualization is fundamental. If you're familiar with NP completeness proofs, the way you prove that a problem is NP complete or NP hard is basically by showing that it can be reduced to another problem that is NP complete through a polynomial transformation, right? So for instance, you know that you can encode a satisfiability problem into a traveling salesman problem, and vice versa, via polynomial transformation. So that's also a form of virtualization. And these are sort of theoretical examples, but at more practical level, you know that any large computing center has a plethora of virtual machines of different kinds. And the window interface also can be thought of a virtualization, right? You have this, for instance, little folders where you put files in, but of course this is just an abstraction. Things like the remote desktop application in Windows, where you connect to a distant machine and you have an interface that gives you the impression that you're sitting in front of the distant machine as if it was right in front of you, is another example of virtualization, etc., etc. So virtualization is everywhere around us. And one thing to notice is that virtualization can create a sense, in some way, illusions, because, for instance, in the virtual desktop application, it gives you the feeling of being in front of the computer which in fact is very far away. And sometimes you forget that you are in front of an illusion. And when you resolve the illusion, sometimes you discover something interesting. And that's exactly what we're going to do to address the deep learning problems that I have described to you. And so I think of these things a little bit like these puzzles or these problems that you play when you're a child, where you, in this case, you have puzzles that can be viewed in two different ways. And both ways are right in front of you under your eyes, but until you see them, you don't see it, right? And it's the same thing that is going on, I think, with deep learning. So for instance, here you have both a rabbit and a duck, but sometimes your visual system gets stuck on just one of these representations and you don't see the other one. And the same thing, those games you play as a child, where you have to find a certain object, for instance, the pencil that you see here. And those objects are just under your eyes, but you don't see them until you get this special sort of a haha moment where you suddenly can see them. So let me give you a few examples of virtualization and sort of discovery of the illusion that is underlying the virtualization. In remote desktop application, for instance, if you want to do a Control-Alt-Delete, which is the Windows command that you execute, that you type in, when you want to look at which processes are running on a machine and to kill them. So if you are in remote desktop and you want to do a Control-Alt-Delete on the remote machine, it doesn't work, because if you type Control-Alt-Delete, it's going to apply to the machine, the real machine that is in front of you, not on the remote machine. And so when you discover that, you have to find what is the right command that allows you to apply Control-Alt-Delete to the remote machine. It turns out to be Control-Alt-End for those of you who are using a remote desktop application, right? So now we are going to apply these ideas to deep learning and to see where is the virtualization in deep learning and why, when we suddenly get out of the illusion, we find the solution to all the questions that I described to you, okay? It turns out that all the deep learning that 99% of the people are doing are virtualizations, right? You use TensorFlow, Keras, PyTorch on your GPUs, etc. But if you think about it, there are no neural networks. There are no neurons and no synapses. What you're running are fantasies of those objects implemented through digital storage, digital code on your computer. So definitely there is a virtualization of neural networks in all the deep learning that is going on today. And so to resolve this illusion, what you have to do is to really go back to the neural level. You have to think that you are a neuron. You have to think that you are a synapse to try to understand what is going on. And so let's do first the exercise at the level of neurons and then at the level of synapses. And that is where we're going to find a lot of insights relative to the questions that I posed at the beginning. So let's first do the exercise of being a neuron. Here are examples of neurons. And imagine that you are one such neuron. And as a warm-up exercise, let's look at the problem of computing parity, right? So imagine you are a McCulloch-Pitts neuron. I give you a strings of 0 and 1s at the input, right? And you have to decide whether the number of 1s is even or odd. You should know that a single neuron cannot do that. It's too hard for a neuron. And for a human being, it is also very hard. Because, imagine I give you a long string with 100,000 0 and 1s. It would be very tedious to count how many 0 or how many 1s are in that string, right? So that's fine. Let me give you another example now, which is computing the connected task on the input bit vector. So what I mean by connected is basically whether the 1s in the input strings are clumped together or not. So if I have a string which has a bunch of zeros followed by a bunch of ones, I should classify it as a 1, right? I can also have wraparound. So if all the ones are at the beginning and the end, that's fine. This is also fine. But then if the ones and the 0 are sort of mixed together, interspersed, then I should classify as a 0, right? And I ask you, can this function be implemented by a single neuron? And is it easy or hard? How does it compare to parity? Your first impression should be that this is much easier than parity, right? If I gave this task to you, would you rather do parity or this? This is much easier. You just look at the string, even if it's 100,000, you look at it, you look where the ones and the 0 are, and you make your decision. So your first intuition is to say this problem is much easier, and maybe it can be done by a single neuron. In reality, this problem is very hard, and it cannot be done by a single neuron. It is basically as hard, if not harder, than the parity problem. The reason you get fooled is because you're using your brain, right? The problem is easy when you use your visual system and your brain, which is a supercomputer with billions of neurons, et cetera, and trillions of synapses, right? But if you put yourself in the shoes of a single neuron, you will see that this problem becomes very hard. This neuron has no eye and no visual cortex, and for instance, doesn't know that the second bit in the string is to the right of the first bit, et cetera, right? It only receives an input string without any notion of sequence, of geometry. And so the problem is much harder, and it has to learn basically what is the particular permutation that is being used at the level of the inputs. So this is an example of something that you understand only when you put yourself in the shoes of a neuron. So let's put ourselves now in the shoes, so to speak, of a synapse, right? And synapses are very small. So it's a little bit difficult to think about them if you're not used to do so. And so what I'm going to do is to rescale synapses by a factor of 1,000,000, 10 to the 6, to give you a little sense of the sizes of these objects in relation to each other. So when you do this, you get the following basically table. A synapse in real size is about 10 to the minus 7 meters. So you multiply by 1,000,000, you get 10 to the minus 1 meters, which is 10 centimeters, which is about the size of a fist, right? So you have wherever you are, take your fist and think of it as if it was a synapse. And imagine that you're trying to play tennis, to learn how to play tennis or to play the violin, and ask yourself, where is the tennis racket? Or where is the bow of the violin? That's very easy, right? Your arm is about 1 meter in length, 2 meters if you're looking at your leg, right? And you multiply this by 1,000,000, you get 1,000,000 meters, which is on the order of 8,000 kilometers, right? So maybe if you are in Mexico City, you see that your the tennis racket is maybe in Tijuana or something like that, right? So how can a synapse decide how to adjust itself, for instance, strengthen itself or weaken itself, in order for you to play better tennis when the tennis racket is so far away? That is really the question that is the center of deep learning, right? This is really what this deep learning is about. What is the algorithm for adjusting synapses that are buried very deep inside a very complex jungle of wires and neurons? The synapse doesn't know anything about tennis. It doesn't know anything about Newton laws of physics, about mechanics. It doesn't have a cell phone. It cannot Google the answer. It is completely blind. It can only see its local biophysical environment. And so it is, in a sense, very about how the synapse can address this problem, right? But what comes out of this is what I call the locality principle, the idea that in a physical neural system, the learning rule for adapting a synapse can only depend on variables that are available locally, right? This is not something you think about if you're doing Keras and TensorFlow on your GPU, right? Because locality is completely irrelevant. Using the transpose of the matrices is very easy when you're doing things in the digital world. Only when you think about the physical neural network level do you really realize that you have this very big problem of locality. And to me, this locality principle is a little bit like the principle in physics, the principle that the law of physics should be the same in all frames, right? The principle that comes out originally was formulated by Galileo. It's a very simple principle. It can be understood by a layman, but in fact, it has very significant and very technical mathematical consequences, including getting to, if you apply to frames that are moving at uniform velocities, you get basically special relativity, sorry. But if you apply it to frames that are in rotation or with accelerations, you can get all the way to general relativity. So a very powerful, very simple principle, but very powerful. And I think the principle of locality is a little bit like that. So let me show you what happens when you apply it to modern deep learning. So how can we formalize the notion of locality when we use the sort of simple neural models that we use today? Well, we're going to say that the rule for adjusting a weight, the delta Wij, the learning rule, has to depend on variables that are available locally, and a reasonable choice of local variables could be the presynaptic activity, the activity of neuron J, OJ, the postsynaptic activity, the activity, the output of neuron I, and then maybe the synapse itself, right? So a reasonable definition should be that a local learning rule for a weight should be some function. For now, let's not worry about the type of function of these variables, of these three variables here. Now, what about the targets? So if you are at the top of a, say, deep feed-forward network, you can imagine that the targets are available locally. They are local variables. And so you can write a learning rule that is a function of the targets, again, the outputs of the pre- and postsynaptic neurons, and maybe the synapse itself, right? So now we have a general form for a local learning rule deep inside a feed-forward network and as well as in the output layer. And we can use that to do all kinds of analysis. So for instance, we can worry about the functional form of the function f. And a reasonable thing to do is to say, well, let's assume that f is a polynomial, perhaps even a polynomial of low degree. So if you say, well, f can be a polynomial of degree 2 or 3 in those variables, you basically can write down all possible such learning rules with a bunch of coefficients and study them in a systematic way. So that gives you a way to immediately see what is the space of possible learning rules, and then to study them in a systematic way if you're interested to do so. And we have done that. It's published in the paper that I'm referring here, in particular in this paper on local learning rule. You can derive tables that tell you what happens with all these rules, etc., etc. I'm not going to go into the details. But the essential point is that this exercise is only mildly interesting, right? You can find learning rule that can do, some simple statistical operation. Oja's rule, for instance, can extract the principal component of the data, etc., etc. But the main point is that with local learning rules, no matter how fancy they are, polynomials of degree 100 or maybe a rational function, trigonometric function, it doesn't matter. If you use local learning rules like Hebb rule, in essence, you won't be able to solve difficult problem in a feed-forward network. So here's why. And that's the answer to one of the questions that I raised. Imagine you have a deep feed-forward network, and imagine that you have local learning rules using the definition that I gave you between the different layers. So for instance, here you have a deep layer of synapses. The learning rule is written like this, and you're free to choose whatever you want. At the output, you're able to use the target. So you have a local learning rule that looks like this. And suppose you're doing computer vision. So you have example ImageNet, right? So you have example of images coming in. You have objects that are targets. You can use a softmax at the output. It doesn't matter. What I'm saying is that you're never going to be able to do well on ImageNet if all you do is this. And the reason is very simple. The reason, if you think about it, is that no matter how complex this rule is, the weights here that you get in the deep layer H are going to depend only on the input. These deep weights are never going to see information from the targets if you're applying local learning rules in a feed-forward networks. In order for the deep weights to depend on the targets, and you can easily show that they have to if you want to be at an optimum mathematically, if you write the equations for the optimum, you will see that the weights must depend on the targets, right? So if you want to be able to have weights, deep weights that depend on the targets, that means that you have to send information about the targets or about the error from the top layer all the way down to the deep weights. Of course, this is what backpropagation does. But again, it's easy to do on a GPU, on a digital system. If you think about a physical system, the question comes up. How are you going to send information from the top layer all the way back to the deep synapses, right? So this explains why Fukushima plus Ebb never worked and why it cannot work. And it also shows you that you need something, you need a channel to send information about the targets, about the errors, all the way from the top layer back to the deep synapses. I call this channel the deep learning channel, the DLC. And a simple conclusion of our reasoning is that a physical system must have a DLC in order to solve ImageNet or to do complex tasks. So if you're dealing with a physical system, biological or other, right, you need to worry about where is the DLC. It's a physical channel in the Shannon sense. It has to have a physical implementation. It has to carry information. So the other question is, what is the information that you have to send through the DLC for enabling learning in deep synapses? And it has a rate, right? A capacity, Shannon again. So every time you think about a physical system, you can ask those questions and you have to worry about those questions, right? Okay. So the conclusion is that there has to be this DLC, this deep learning channel for optimal learning. In a physical neural system, there must exist a communication channel that conveys information about the targets, the errors, to the deep weights, resulting in local deep learning. If you think about biological system, by the way, this gives us an important insight on the notion of feedback, etc. We know that in biological system, there are actually more wires going in the backward direction than in the forward direction. So those could perhaps be part of the DLC. But very often we use the word feedback in a sort of ambiguous way, because there is a notion of fast feedback, right? Where, for instance, in the visual system, you may have activity going from the bottom, from the input layers, from the retina, the LGN, V1, etc., towards the deeper areas. And you may also have sort of top-down expectation that are propagating in the opposite direction from the deeper centers towards the periphery. And you can imagine these two streams need to interact with each other in order to stabilize your perception, etc., on a fast scales, on the order of tens or hundreds of milliseconds, right? So that's one idea of feedback, or in a motor control, where you have very fast feedback based on activity and not necessarily on learning. The DLC is about learning, so it's feedback that could be slower, that occurs on slower timescales, where information is propagated from target layers, where you have a notion of error, all the way back to deep synapses. These two different signals could use the same connections or could use different sets of connections. We don't know that for a biological system, but it's definitely something to be aware that there is these two completely different kinds of signals propagating in the sort of backward direction. The other interesting conclusion that comes out of this analysis is that if you believe that backpropagation is plausible, that biological systems are doing something like that, and again, that's a question that is not settled, it basically predicts that you have a DLC going back from the periphery to almost every synapse in the brain, right? So it's a very strong prediction, again, from a very, very simple principle of locality. Okay, so the DLC, you can ask where is it, where it is, what does it, what information it's sending, how is it sending, etc. What is the capacity? Of course, these questions have to address, ultimately they have to be addressed in a physics-dependent way, depending on which physical system you're using, whether it's a biological system, whether it's optoelectronic or whatever. The answer is going to be, of course, different. But you can show also that, at least conceptually, backpropagation is essentially optimal because it sends the best possible information, which is the gradient, the best direction for incrementally optimizing the weights, using only OW operation, one operation per weight, essentially, with the big O notation. And you can show that you cannot do better than that. This is the minimum that you have to do, right? So there is definitely a sense in which backpropagation learning is optimal. And so you can expect that ideally DLCs, whatever their implementation, should try to do something that is close to backpropagation. So, of course, the question comes up of, how can you implement backpropagation in a physical system if you cannot transpose the forward matrices, right? If you cannot ensure that the weights in the backward direction are identical to the weights in the forward direction. So let me show you a solution to that problem that comes by looking at backpropagation in this form, which is what I showed to you in a previous slide. And if you think about it, and you look at the backpropagated error, you see that it is a product of many terms, where you have the transpose of the forward matrices, which are changing in a somewhat slow scale, especially if you're doing batch learning or, depending on the size of your batches, this matrix doesn't change over an entire batch. Whereas, or if you do true gradient descent, whereas the derivatives of the activation functions are changing very rapidly. For any given example, these derivatives are changing. And so in a sense, you can think of this matrix as being somewhat random, a matrix that is fluctuating somewhat randomly. And one idea would be to replace it with a random matrix. Okay? And that's the idea of random backpropagation. It was presented first in a paper by Lillikrab and collaborators, where the idea is to, instead of using the transpose of the forward weights to propagate the error, is to use completely random matrices and see what happens. And the amazing thing is that it works. You can put completely random matrices on the way back, and you still can show that the system, through simulation at least, the system can learn. Of course, if this works, it completely addresses the problem of having symmetric connections in the backward channel. Now, when you think about random backpropagation, of course, there are many, many possibilities, right? How do you choose your random matrices, right? They could be Gaussian, they could be binary with coin flips, etc., etc. You could use dropout on the way back. You could use the derivatives of the forward activation or not use them. You could imagine that the weights in the backward direction are adaptive themselves, are changing with some learning rules, so that they are operating in the same way as the forward weights. Otherwise, you need to postulate two different types of matrices, the forward one which are adaptive and the backward ones which are not adaptives, etc., etc. You can also have skipped connections, where instead of propagating the arrow back in a random way, layer by layer, you could go directly from the top layer to a deep layer via a random matrix, etc. So there are literally dozens of variants of random back propagations, and we have studied all of them in detail through simulations and in some cases analytically. And the bottom answer, the high-level picture, is that they all sort of work. You can see here, these are examples. We did experiments on NIST or CIFAR-10, for instance. And you can see that most of these variants of random back propagation are capable of learning the data. So the general idea of using random signals, random matrices on the way back is very robust to all these variation. And so I would argue that the DLC is actually very robust, and most of these combinations work well. In some cases, you can actually prove it mathematically. And again, I won't go into the mathematical details, but you can look at our references. And finally, there is a particular architecture, which is called the circular autoencoder, where you have an input layer and you go around and you come back to the initial layer. This is why it is an autoencoder. So you can imagine that by the time you go once around the loop, you could compute an error function here in this initial input layer, right? You can have bottleneck layers around the loop if you want to do compression, etc. But the point is that if you think in terms of DLC, when you have an architecture that is circular in this way, you have a forward channel that propagates your information forward. But if you think about the DLC, you could imagine using the same channel to transmit error information or target information for learning. So in this case, you don't even need to have a secondary channel like random matrices in the backward direction for learning. You could imagine trying to learn everything using only the forward connections. And the way to do that is that you, in the most simple form, there is many variation, but in the most simple case, you just send the information around the first time, then you send it around the second time, and you imagine that the first pass is the target for the second pass. That's the original idea of the recirculation algorithm introduced in the 80s by Hinton. But using ideas from the DLC, this can be studied at a deeper level. Again, we have mathematical results on this, and you can see that this is actually a variant of random back propagation. So I would say that recirculation, all the recirculation algorithms are actually special cases of random back propagation. So this is a summary of sort of the sequence of main ideas that I've described to you. And again, I refer you to the papers for more details, simulations, and mathematical understanding. Everything comes from the basic principle of locality. Learning rule for synapses have to be local in a physical learning system. And unless you think about virtualization, most of the time you live in an illusion. You're not thinking about a physical neural system. You're just thinking about the digital simulation of the physical neural system when you're doing standard deep learning neural networks on your digital machines. Thinking about locality immediately gives you a sense of what is the space of possible learning rules. It helps you identify why backpropagation is optimal. It explains why Hebbian learning never worked in the original convolutional neural network architecture of Fukushima. In order to learn, you need a DLC, a deep learning channel, in a physical neural system. This raises the question of why, how can you deal with symmetric matrices in a physical neural systems? One possible solution is to use actually random matrices, which is very surprising, but that's the idea of random backpropagation, and it works. It is a physically plausible approach to applying backpropagation in physical neural systems that cannot transpose weights, cannot transport weights. There is an interesting mathematical connection behind all this to Hilbert's 16th problem, which is basically solving different polynomial differential equations, which is a very difficult problem and still open. And finally, you can look at recirculation algorithms, where because you're looking at difference between the first time around the circle and the second time, what you get is a notion of locality in time. You have to remember the results of the first pass in order to implement the corresponding learning rules. So learning rules have to be local both in space and time, and recirculation is a nice illustration of what locality in time could be. And it's also a special case in a sense of random backpropagation. So to summarize, I raised 4 fundamental questions about deep learning. All these questions are difficult to answer when you are in the virtualization, the digital simulation of neural systems. Once you start thinking about physical neural systems, you see immediately the locality principle, how important it is, and you come up with a solution, a good answer, I think, for these 4 fundamental questions. Looking a little bit at the future, if I had to speculate, I think that virtualization is going to remain an important guiding process, an important guiding idea in AI for future progress. Sorry. I think you're going to have a situation where you have many agents or processes that are capable of emulating each other, or one process being able to emulate another process. This could be within, let's say, a brain where you have different systems, and one system being capable of looking at other systems and emulating them, or of course across different systems, different agents, different brains, etc., etc. And I think we do have a challenge or a handicap when we're trying to uncover these virtualization operations that may be going on in biological system or other system, because again they are opaque to our introspection. So it's back to this idea of illusion, and until we see things in a sort of a clear way, we are going to have a challenge in trying to uncover these levels of virtualizations. And we can look at what happened from evolution, and I will finish with a little story, which is a theory. It's not by any means proven, but it gives you a little bit of hint of what could be happening. And if this theory is correct, you will see that virtualization had a fundamental role to play during evolution of the brain and during the evolution of the intelligence. And the idea is this, is that one of the major breakthrough during the evolution of intelligence was the transition from cold-blooded animal to warm-blooded animals. So going from basically from crocodiles to mammals, if you want, tens or 100 million years ago. And the issue is that a warm-blooded animal needs 10 times more energy per pound of weight than a cold-blooded animal. So if you need 10 times more energy, you need to be very adaptive, very smart. You have to be able to navigate different environments in order to acquire the food that you need, right? The energy that you need. So there is really a jump of intelligence that occur there. And there is a big problem, because if you are a cold-blooded animal, if you look at cold-blooded animal, they don't seem to care very much about their offsprings. The offsprings are born almost fully functional. If you look at turtles or crocodiles, they can swim very early and obtain the food and the energy that they need very early after birth. On the other hand, for a warm-blooded animal, there is a long period of learning that is necessary in order to become, more intelligent. And so the offspring of warm-blooded animals are born fairly helpless. Humans are completely helpless for several years, and so how do you take care of an offspring that is completely helpless for several years if the mother or the parents are cold-blooded and do not care about the children, right? So one idea is that what happened is that the brain of the warm-blooded mammal basically started feeling the pain of the offspring, of the warm-blooded offspring, as if it was her own pain, right? And if a warm-blooded animal feels the pain of an offspring as if it was her own pain, of course, it will do something and start caring for the offspring. And so for this process, feeling the pain of the other in a very strong way, it's of course a process of virtualization, which is at the root of empathy, etc. You have to be able to simulate the brain of the offspring somehow and the situation of the offspring, so that when the offspring cries, for instance, you sort of feel a pain and sort of a force to try to alleviate that pain and to take care of the offspring. This has been put forward by Pat Churchland and others. Again, it is a theory, not everybody subscribes to it. But if it was true or had some elements of truth, you can see how during evolution, this issue of virtualization, of having one brain being able to simulate or emulate some other brain or some other situation may have played an important role. And thus one can guess that this sort of things will also play a role in the future of AI. Thank you very much, and let me try to address some questions. Thank you.
Thank you very much, Pierre, for this interesting talk. We have some questions, and I will start with the first one. Carlos Castro comments, "Thank you for the conference. It opened my mind to a bunch of terms I was not familiar with. How much do we need to understand about our brain to improve virtualization and artificial intelligence?"
Well, that is a very tricky question that comes up all the time, right? Should the future of AI be guided by neuroscience? I think it's a fundamental question. Every scientist has to make a choice on that spectrum. So if you're asking my personal opinion, I think that there is still a lot to be learned from biology. I don't think we have extracted all the trick that we need for building more intelligent systems. But again, some scientists disagree. Some scientists think we just need to scale up deep learning with more GPUs and more data. My intuition is that that is not enough, but it's definitely a question that you should think about. And it's a difficult one because biology is very complicated. So if you study neuroscience, it's full of complex details. And the question is, which of these details are really important and which are somewhat irrelevant and related to the fact that biology has to use basically carbon-based computing, so a very different type of hardware compared to silicon, right? But it's a good question, of course.
Thank you. Raul have another question. Is there any relevant knowledge about the backward channels in the human cortex that could be exploited in deep learning?
Yes and no. In terms of anatomy, as I mentioned, we know that there are more connections going in sort of the reverse, in the backward direction, than in the forward direction. I think the ratio is like 1/3 to 2/3, something like that. So definitely those could implement the DLC, could be used to implement the DLC. There is, of course, tons of literature on learning algorithms at different scales at the level of what happens inside synapses biologically, biochemically, what happens at the level of electrical signals of, spike and spike trains, etc., how close they have to be in time for learning and for potentiation, etc., etc. So there is literature, but in spite of all the literature and everything, you get a sense that we don't really understand how learning is implemented in the brain yet. Not well at all.
Thank you for your answer. Cristian Ocaña Bautista have another question. Hello, I am a bachelor student, and in the future, I intend to obtain a master's degree in this science. I would like you to recommend a collection of books to start with it, and what mathematics knowledge is essential to master for understanding them. Very interesting question.
Well, I will embarrass myself by recommending my book, which is not out yet, but if you send me an email, I'll send you, I can send you some chapters, but there are other books out there, so you should do your own literature review, but I will shamelessly recommend you my book. In terms of what mathematics, again, it depends at what level and what kinds of things you want to do. There is a little, you need to know, I would recommend studying all, the basic mathematics you should learn in college. So basic calculus, basic probability, basic combinatorics, basic optimization. Those are definitely useful. Differential equations. If you want to understand things mathematically, those are and of course linear algebra. Those are the basic things that you should study and use. But then if you start working in particular areas, you may need also more advanced concept. Information theory is also, of course, something you should study, and it's very useful to better understand deep learning and neural networks.
Okay. Let's continue with another question. Enrique Zucker says, regarding backpropagation with random matrices, this have to be a random, or there could be a deterministic?
They can be deterministic. They don't have to be completely random. Of course, they cannot be all zeros, for instance, right? So there are some constraints, and if you look at our papers, you will see a little bit more about that. But yeah, you could pick up a deterministic matrix and it may work, or set of matrices and they may work. Yes.
Okay, thank you. We have a question.
Let me just add something. Also, another thing I want you to notice, random backpropagation is something that nobody uses in applications, right? Because again, on your GPUs, you can use a transpose and everything is fine. Nobody is going to think or use random matrices to do backpropagation in all the applications you see. Furthermore, it is true that if you use random matrices, things are a little bit more difficult. They converge more slowly, etc., etc. It hasn't been, completely studied in detail. But so again, because of the virtualization issue, random matrices are interesting only for people interested in the theory or people interested in physical neural system. For practical purposes, for applications, so far, there is no examples that I know of where using random backpropagation is helpful to you. So again, almost nobody uses random backpropagation. That doesn't mean it's not a very interesting concept, of course.
Okay, thank you. We have another question. Alpha Kumol Tech, this theory can be applied to quantum machine learning?
I don't know much about quantum machine learning, but I think the locality principle is a general principle that applies to physical systems in general. So, in that sense, I think there should be something about of that nature that can be applied to quantum learning. But again, I'm not an expert on quantum machine learning.
Okay, thank you. I have a question. What do you think is the most important advance in deep learning the last years? What do you think about? What do you consider is the most important advance?
Well, it depends what you call the last years. Everything you see today, what really makes it work is basically the fact that we have GPUs, the fact that we have abundant amounts of data of all kinds through the internet, databases, et cetera. And it's also very helpful to have, very good software libraries that are, very robust and maintained by companies, by industry, like TensorFlow and PyTorch. That's certainly very helpful. But other than that, all the things that you hear about today that are claimed to be major breakthroughs are really small incremental things. We were already training networks with hundreds of layers in the 90s without any problems on CPUs. So I don't think there is a major theoretical breakthrough, but again, I think having GPUs, having data, and having software libraries are really the three main ingredients that make deep learning so useful and so widespread in technology.
Okay, thank you. Another question. What do you think, or what are supporting deep learning to address actual problem like the pandemic that we are living right now? What successful results have obtained by using deep learning to address COVID-19 pandemic or something like that?
Well, I've seen people who have done a little bit of that, but I've seen groups applying deep learning, in very different areas. You can apply it to, for instance, you could apply it at the molecular level in drug discovery, trying to find new drugs for COVID, trying to better understand COVID proteins, for instance. So that's at the molecular level. You could try to help the effort to find better vaccines. And then at the other end of the spectrum, you can apply deep learning to the literature on COVID and related viruses and related biology, or you can apply it to data from social media, or to monitor how the disease is spreading, et cetera, et cetera. So people are doing that. They're working with natural language, with text. They're working with protein sequences, all kinds of different representations. In the short term, I think, from a scientific point of view, what we need the most is a vaccine. We're told that vaccine should be available in the coming months, and that was not done using deep learning, as far as I know.
Okay. Thank you very much again, Pierre, for your interesting talk. Of course, thank you very much to all the attendees that I followed this interesting talk. And I asked to Enrique Zúcar in order to share information about the next talk in the frame of this national colloquium. Please, Enrique, the floor is yours.
Yes, hello everybody. I want to invite you to our next talk that is going to be in around 1 month, presented by Dr. Adam Darwich. He's a professor in UCLA, has got a lot of contributions in symbolic and probabilistic reasoning, and is going to talk us about tractable reasoning and learning with arithmetic and Boolean circuits. These type of systems are very interesting. They can have maybe a bit in between graphical models and deep learning, are very efficient, more efficient than traditional graphical models, but at the same time, they can allow to reason and a bit explain their conclusions. There has been a growing interest in these systems, and Adam, that is one of the founders of this area, will talk us about their background, their foundations, and some applications. So you are all invited. This will be November 25 at the same time and by the same channel.
Thank you very much, Enrique. And thank you again for Pierre. Thank you for all the attendees. And see you the next month with the talk that have present Enrique Zúcar. Thank you very much again, Pierre. See you soon.
Muchas gracias.
Muchas gracias.